Thank you very much for your invitation. So I did stick a little word in front of my title, and first would like to explain the title a bit. When I talk about quantum simulators, I mean tabletop experiments, so analog simulators and using quantum systems. And the reason why there is a two words, because these ideas have not been directly implemented. We are currently about to do that. And the kind of physics which we want to see, I'm calling it fundamental physics, but I'm going to talk about what kind of fundamental physics I have in mind, which is linked to a gravitational system and cosmology. Besides myself, there's a number of collaborators within the UK and abroad, and I'm going to list them according to the topics. Okay, so what's the motivation? So just to put it into the bigger picture really here, so we're interested in the dynamics of the early and late universe when both quantum theory and gravity matter, and in particular we are interested in the interplay between these two fundamental theories. So there is, however, a predicament or an issue here, and that is that there are a bunch of very important or essential processes that we predict, or we have as a result of calculations, we know that they should arise, but in situations that are difficult or perhaps even impossible to experiment with or to observe. And there are situations where these calculation techniques or our conventional calculation techniques break down. So what are these situations? So there are when the gravitational interactions are strong, when quantum effects are important, or simply if you look at scenarios that go beyond the length scale of our observable universe. So yesterday, in the past few days, there were a debate about using analogs and what you can learn from them. And I'd like to be very, very clear what I have in mind with this. So what we are dealing with are analogs in the sense that there is a mapping of the dynamics or a subset of the dynamics in these analog systems to quantum field theory in curved spacetime. And so, of course, when you start with this, you're assuming that quantum field theory in curved spacetime is a good approximation. So what one cannot do is one cannot verify if quantum field theory is a good approximation. So the assumption is that at least to leading order, this is a reasonable theory to work with, right? But then there is another caveat here. So we never verify an equation. That can't be done. What do? You have a theoretical model, then you solve it, you derive some observables. And of course, these observables are there and the experimental verification is there to sort of verify the underlying theory and to see these processes. But there is another question mark here. Sometimes when you apply your calculations, it's not clear if your approximations are actually valid. And this is what these analogs are for. They should help you to learn how to solve these equations and to see if your mathematical toolboxes are working. And they should inspire then, once we improved our modeling of the system, we should go back to the gravitational systems, refine the modeling. And so what the idea is here, that you turn a range of abstract ideas into reality, and by doing so, you have a cross-validation as how we extract information from these theories. That's the hope. And then beyond that, and I will come to this, go a step further, and perhaps by developing this cross-validation, this theory experiment loop, can you look for new effects? And I will talk about this in this talk as well. Okay, so this is sort of there's this problem that there are these interesting effects which we simply cannot access observationally or experimentally. But we would like to introduce sort of this feedback loop to at least test if the way we solve the equations or the theory we work with, if these assumptions and simplifications, if they work. So how can we do it? Well, there is a class of laboratory systems which are completely non-gravitational, But if you look at small fluctuations in these systems, their dynamics is governed by effective relativistic quantum field theory in flat or curved spacetimes. So that's sort of in a nutshell what these analogs are about. So what are these systems? These are down-to-earth systems. And so what is depicted here is this fluid in a box, in a bottle, and then you see all these cosmological objects that sort of captures the spirit. So what we're looking at are a variety. It's not one system and it's not one for all, but depending on what you're interested in, you can work with fluids or superfluids, can be fluids of light, Bose-Einstein condensate, superfluid helium, optical systems, and so on. So here I depicted it here. So on the top here, one can look at air-water interface waves on vortex flows. Here you see a nanofluidic chip for superfluid helium-4 films. And below you see ultra-cold atoms experiment, a typical one, where you manipulate pure superfluids, the Bose-Einstein condensates. And what is bringing all of these things together is that if I look at the dynamics of the equations, they're all described by quantum field theory in classical, if it's a classical fluid, don't get me wrong, but by in the superfluids is then a quantum field theory on an effective curved spacetime geometry. And this is what unifies all these systems. And this is why you can use these as analog gravity systems or quantum simulators for gravitational physics. Right. So how good a simulator is always depends how versatile it is. So when you, I think also Jacopo gave this very nice talk opening the conference, in fact. And so he already mentioned some successes in the field. And most prominently is Jeff Steinhauer's implementation of Hawking radiation in one-dimensional Bose-Einstein condensate. Now, what is this all we can do? So how much more and what can actually be done with this kind of class of simulators? So how many knobs do I have to adjust and set up different challenging situations on a tabletop, on an optical table, for example? Now, what you can do, and this is a realization sort of over the last years, if you step up a bit, and if you say, well, I don't need to only work with a single superfluid, I could work with multi-component superfluids. And why would one do that? Well, these multi-component superfluids, they're interacting with each other, as well as each one has its own accessible parameters. So you're more than doubling the parameter sets, the knobs you can turn. Now, if I take all that's possible, at least on a piece of paper, into account, what can we do? So the first thing is you can say, well, what kind of space-time geometries can I set up? Well, I can set up, of course, flat space-time, and that's not boring, that's very important. That's a lot one part of the talk here. Of course, this is just to put you back into these pictures of fluids, just a fluid at rest. You can set up black hole horizons if the fluid flow goes supersonic. You can set up cosmological scenarios when you dial the sound speed as a function of time, when you change it. And if you, for example, just to give you an impression here, if you look at sound waves and you say, well, how big for a sound wave is the system, the finite size laboratory system it's in? How big is the BSE, for example? Then it depends on its propagation speed, the time it takes to go from one end of the experiment to the other. And so if you exponentially change, for example, exponentially decrease the sound speed, in a way, this effective universe, these sound waves and these fluctuations experience are exponentially expanding. So this is just a bit to give you an idea. Now, this is all sort of more or less known, but then by adding multi-components, you can actually drive, or the hope is to drive inflations long enough that you see effects like mode freezing in the system, where you need several e-folds in change of the size of the universe within a blink of an eye, because you know this tabletop experiments, this superfluid exists for microseconds. So now you can not just look at different geometries, but you can also go and look at the signature of space-time. And you can actually manipulate the space-time, the signature of the space-time, through some external fields. For example, you can switch from Euclidean to Lorentzian geometry, and what it means, you change from hyperbolic equation to elliptic equations. Now, of course, elliptic equations are not stable, but you can actually also stabilize this system to some extent. And you could think about this as sort of an initial state, where then as an elliptic system, like you have an Euclidean geometry, and then you change, and then you could start that as the beginning, the initial state of your evolution of your cosmological scenario. You can also set up massive modes. What does that mean? And I have to first say, what is the analogy really? So you have scalar fields, usually massless scalar fields, that minimally coupling to an effective space-time geometry. And what you can do, again, with multi-component fluids, you can actually add a mass term to the system. And then what you can do is you can make this mass term stable, but you can also make it unstable. And unstable means that the mass squared is negative. So I have an imaginary mass. It's a tachyonic field theory you can play with. And what I'm going to talk about is in between. You can make it metastable, and we use this to explore the false vacuum decay. And last but not least, these are actually down to earth physically systems. And now the necessity of having something that interacts with this and building a detector is becoming an actual requirement. And one of the next things we're doing now, we're developing detectors, local probes. And as I will show, these local probes, they act like effective anode detectors. So this is what can be done. And now you have to go beyond just having the fluids. You have to think of how other fields are interacting with your quantum simulator. And this whole slide and this very long discussion was just to make a point here that what has been done over the last years, in theory, we have understood and characterized the similarities and the differences, and to provide high-level modeling for these analog gravity simulators. And we have had significant successes in the lab that validated this approach. It does work. And the next step is to apply it and to go one step further and try to explore situations where we have question marks, which mainly come from the modeling, but also can we put ourselves into an unknown territory? So I have problems. Okay, I hope my computer is not switching off. If it does switch off, because I have problems with my battery last hour. If it does switch off, you should just continue with the next talk because it might take me long to get back. Now, let's hope everything goes well, and I don't have to stop here. So what's the idea? We want to investigate two different strains. We want to focus on the quantum vacuum fluctuations in these analog gravity simulators. And we want to look at quantum black hole features, and I get back to that, what I understand as a quantum black hole. And so in these two areas, in the quantum vacuum, we want to look at the false vacuum decay and at the observer dependence. And in the quantum black hole, we want to look at an effect that at first people would not at all associate with a quantum effect. We want to look at the black hole ring down. So let's start. Just look at the time. I think I'm doing well. So the first topic is the false vacuum decay. So the false vacuum decay is a phase transition. It's a first order phase transition in relativistic quantum field theory. So why is that interesting? So this is a statement about the initial state of your field theory. So suppose you start with a relativistic field theory, but it doesn't start with the right foot. It starts in what we call a false vacuum state. So it's not in the lowest energetic state. There are lower energetic states, and there is perhaps a true vacuum. But let's say it starts sort of in this local minimum. And so what happens to this relativistic field theory, it will not remain there. The prediction is that it will actually decay. and eventually decay in a true vacuum state via what we call a bubble nucleation process. And so this kind of effect, strictly speaking, goes beyond what we have focused on in analog gravity studies so far, where we looked at non-interacting linear field series, and that is in spirit, also where Jacopo was hinting at in his talk, where he said, what about back action? Or what about the situations where we get out of the things we understand quite well? And particularly going into back action or nonlinear effects is really where our methods are less predictive. And it's harder to really get a good grasp on the calculational techniques. So this is a first order phase transition, non-perturbative, non-linear, non-equilibrium process. And what we hope to set these simulations up into time domain to have a time evolution of this process, rather than just looking at decay rates, as for example in the instanton calculation. So now I have a few minutes to explain you how you could get something like this from a multi-component superfluid. And I'm going to do this by arguing about symmetries. So what we have, again, I said, like, you needed more than one fluid. So we take a 2-fluid system. So let's make it as simple as possible because I don't have much time. Let's just pick one example, which is not the only way to do it, but one example. I am working with a Bose-Einstein condensate, and I have 2 different kinds of atoms. So I depicted it here as the turquoise and the bourbon atoms, or purple atoms. And so these are 2 different atoms, and for sake of making it a bit more real, we have rubidium-87 in 2 different hyperfine states. Okay, so this is all I have. I have a mixture. They're not separate, they are mixed. And now what can happen? So I wrote down the Hamiltonian density here. Well, it's a non-relativistic Hamiltonian at that point, simple system. You just have a kinetic term, right? So I have here this psi i's. These are just the boson creation and annihilation operators, a many-body quantum system. So they have a kinetic energy. They are trapped. They're in a box. It's a finite size system. And then this is an ultra cold, highly diluted gas of atoms. And what that implies mathematically is that I only consider collisions between two particles. They come together, they scatter off, S-wave scattering, and then they leave again. To form a molecule, you would need collisions of 3 atoms. So, but it's so diluted, it's just unlikely that this event happens. So you have this simple or simplified interaction Hamiltonian term. And so you have these DIJs, these are just the interactions between the different atoms. So now there is, if you look at that Hamiltonian density, you will see that the Hamiltonian has a symmetry. And these symmetries, if I take my boson field operators and replace them by field operators times e to the I, phi, some constant phase, there's a symmetry. And we know from the Nambu-Goldstone theorem, sorry, we know this. Now, if you form a Bose-Einstein condensate, it undergoes a spontaneous symmetry breaking. The symmetry is broken. The BEC itself, the condensate, has a density and it picks a phase, a random phase. And so what that means, there's the Nambu-Goldstone theorem, is you get massless bosons, massless modes, which are the sound waves in the system. If you have 2 components, 2 BSCs of this kind, you will expect to get 2 massless phonon modes. If you now break explicitly this symmetry by adding another term to your Hamiltonian, which basically just drives transitions, which are, for example, called Raman transitions between the different hyperfine states. So you turn a turquoise to a bourbon atom. You can drive a transition simply by interaction with a laser field, external laser field. You break the symmetry explicitly. And this is how you can get around this Nambu-Goldstone theorem. And what you do, I want to give you an idea of what kind of excitations you get, and then I'm going to bring you back to the false vacuum decay. Why is that important? If I have a single BSC, I can explain actually the excitations in such a BSC with a simple mass spring system. If I have a single BSC, I can have a massless excitation. If I have two coupled massive with a spring, I can have the breathing and the anti-breathing mode, the massless and the massive mode. If I have three coupled, again, I have a massless mode, and then I have two different massive modes. And this is how you should think about what the nature of these excitations are. There's also a geometrical picture in there, but one has to be careful, because as I sort of indicated yesterday, what you get is a Fenslerian spacetime geometry, which can be fine-tuned to bimetric or monometric, multimetric series. But this is just a side remark and not important here. So what it means, I can create a massive mode. That's all I've done now. I've added, by adding this complication, by adding this transition, you can create massive modes. What is the fantastic thing, and I mentioned that at the beginning, you can actually create this mass stable or unstable. And so here you look at the dynamics of the relative phase fluctuations in the BSC, and they exhibit a Sine-Gordon Lagrangian. And now where you are here in this potential, you can experimentally tune yourself. They can actually do this in the lab. And you can put yourself on the top of this potential, then you have a tachyonic field theory and will just roll down that potential. You can put yourself in the minimum, and then you have a stable massive mode. That's all it is. So, and now we have this system, and what we want to do is we want to put ourselves on the top of this potential. This is, remember, tachyonic field theory. But now what we're going to do, we want to make it metastable. So we need to deform this potential to have a local minimum here. And the way we do it is a very weird thing. If you think about it, you have something that's highly unstable, and you're going to hit it with a hammer. But you hit it with a hammer so fast that it stabilizes it. So what do I mean? When you have these transition rates between the two different atoms, you put the sinusoidal modulation on top. And this sinusoidal modulation has an amplitude. So you don't have a constant transition rate. It's modulated. It's a very high frequency so that you can integrate it out. So you put a high resonant frequency, a parametric resonance on top of it. So what Jacopo presented was not of that kind, but he looked at parametrically excited BSC, and you can grow exponential. Modes can exponentially grow. It's an instability. But here what we suggest, you make that so high, you tune a very high frequency so that it doesn't drive its own dynamics. Instead, you can deform this potential. And how does it work is similar to this here. That explains how this works. It's an inverted pendulum. And what the guy shows, if you have a pendulum, oh, I need to, sorry about that. I need to, okay. So I have this inverted pendulum. Of course, if you're upside down pen inverted, it is not stable, it just fall down. And what he does as the next step, he adds a high resonance frequency, and this is stabilizing the system. So this is what you do in these BSCs in the same spirit. And now I need to just find a way to go to the next slide. Oh, excuse me, and I have to, sorry, computer problems. So here's what we have. Let me, so I'm sort of moved, I made a big mistake. I moved the people around now, they're in the middle of the slides. Okay, so what you can do, and now I have to really ramp up a bit. So what you see here, these are different scenarios for the amplitude of modulation. And what you see, if the amplitude is 0, right? If you you don't have a modulation, just a constant rate, you have a tachyonic field theory. This at the moment, these simulations are in 1+1 dimensions. So you start out, blue means in the false vacuum, and immediately you have this decay, which is depicted, the red areas means you're out of this true vacuum state. If you increase this amplitude, you see this change happening. And if you go, for example, at the last instant here with the highest amplitude, you see that you get a decay from the blue to the red, from the false to the true vacuum. And what you see is this is sort of here, it propagates out with the effective speed of light, the sound speed here in the system, and it has sort of this cone structure. And if you go in higher dimension, it's this bubble. And what you have, you can tune, you have a parameter where you can tune from a second order to a first order phase transition. And so what is also really important for these experiments is that you can influence by shaping the potential, you can influence the nucleation rate. And that's important because these experiments happen in milliseconds, and you cannot wait for the lifetime of the universe for this decay to happen. So it is also a matter of setting the system up in a stable way and then controlling it to such a high extent that you can have this nucleation happen in the lifetime of your experiment. So who is going to do this? This is in the UK, that's Zoran Hadzibabic. The reason why he's the ideal candidate to do this, over the last years, Zoran developed what is now commonly referred to as a box trap. And what he can do, he can trap a BSC, a 2D BSC in a box, meaning that it is almost homogeneous, homogeneous to a very high extent. And what this experiment is about is the control in the background, the control in trapping it, manipulating it. This is where the challenge is. Okay, now observer dependence. We have talked about the high control, which with the help of quantum technology, how you could control these superfluids to an extent that you can set up metastable states. And now we talk about, well, how do we actually interact with your quantum simulator? And I want to just to explain how I see the situation, perhaps coming from an experimentalist viewpoint. If you have a quantum simulator, right, means you have a quantum simulation in the time domain. And of course, ideally, you want to interact with your quantum field theory in a minimum way. And a perfect probe would be one that is a quantum sensitive probe that doesn't, because if you interact with your superfluid, you ultimately destroy it. You destroy the quantum effects, the quantum coherence, and all the things in the system. So in order to get really a nice evolution in time, you want to develop local detectors. Now, and when you anyway should do that, you can also ask, well, what does a local detector see? Because there is such a thing that's called observer dependence. Now, what's the observer dependence? There's this very famous formula derived by Bill Unruh in 1976. And so what we have here is he says, well, if I have a uniformly linearly accelerated observer, and they're coupled to the vacuum fluctuations of the Minkowski space, of the fluctuations of the Minkowski vacuum. What he will see is he will see not the absence of particles, but he will see a thermal radiation. And this thermal radiation is now commonly dubbed as the Unruh temperature, has a very beautiful, simple expression. And that simply says it is equal to h bar over 2 pi. Okay, these are just constants, but here you have a, which is the acceleration of your observer, divided by c, which is the speed of light in this case. Now then, in order to do this, to derive this, Bill looked at what I would say it's the essence of a detector. It's the simplest detector you could mathematical, or the most sensible, but still the simplest or the most approachable detector, which is a 2-level quantum system with an energy gap. And this detector that acts on a smooth time-like trajectory, yeah, and this is parameterized with the proper time tau. So what is a proper time? Well, it's right, just a time along a timeline world line. And so this is the time measured by a clock on that world, on the time-like world line. And so you couple here, this interaction is very simple. You have an alpha interaction coupling constant. You have a smooth switching function that you can switch the detector on and off the coupling. And then you have a monopole moment of the detector and then the quantum field you're coupling to. Now there's a caveat here. So why has this, what I would say, the zeros, one of the most basic effects, how do we perceive the quantum vacuum? Why has that not been seen? Well, the reason is because of the smallness of the temperature. So if you put in the numbers here, and unfortunately you divide it by the speed of light here, which is a large number, but if you put in the temperature, what you get, it's 2.5 times 10 to the minus 20 Kelvin per acceleration. So this is a very, very small effect. And when you derive this equation, when you derive this, there goes a lot of assumptions in there. So it would be beautiful also to see if all of this assumption we put in there, if they actually work, and if you go away from point-like to extended detectors and so on. So here's our proposal. So in order to set this up in an analog gravity experiment, what do we need to do? Well, the first thought we need to put in, there is no analog of a relativistic proper time. The solution is, instead of linearly accelerated, go on a circular trajectory with a constant velocity, but the fact that you change the direction all the time gives you the acceleration. Now, the physical system, so a two-level system, you could set up a two-level system, but again, perhaps from an experimental point of view, what is your detection scheme? You need an actual detection scheme. And so our solution replaced a two-level quantum system with an interferometric setup. And so this is completely different now, because we sort of had to free ourselves from the idea that you work with these gut systems. And instead of that, you work with a continuous probing field. So you have your superfluid, and I'm going to explain it, and then you have a laser beam interacting with it. And this laser beam is my detector, but this is a continuous electromagnetic field. And as we will show, the effect, if you work out the effective field theory, it is a suitable Unruh detector. Now, what is wonderful here is because how does it look like? We were talking about the smallness of the effect, and it's still small, but there's one advantage here, because the speed of light is replaced by the speed of sound in the system, and the speed of sound is millimeters per second. So in order to see the relativistic or the Unruh effect in an analog gravity system, you need to go with the speed of millimeters per second. So that can easily be implemented. You don't want to go supersonic. There are many problems there. So, and you have just, that gave you 11 orders of magnitude. So this is something that's sort of a present that comes out here. And so I need to move on. Really, I don't have so much time, but I want to explain you just the in a nutshell why it works and how simple it really is. So we're talking about interferometers, about optical interferometers. And to explain the main principle, I made it simpler, and I relate to something everyone has seen, which is a Mach-Zehnder interferometer. And so what we have a beam splitter 1 and a beam splitter 2. So an optical interferometer, you need to divide and recombine an optical beam, a laser beam. And you do this with beam splitters and mirrors. On the bottom here on the top, these are mirrors. So from the left bottom half here, I have a laser beam coming in. Beam splitter is a 50-50 beam splitter, let's say. It doesn't matter. It could also be any other way. That is not important. In fact, you don't want it 50-50, but that's a technical detail. So you split it, and one goes up on the upper branch here, and the other one goes on the lower branch. And for a second, think that this green thing here is not here. I'm going to talk about this. And what we're going to do, we're setting it up. You recombine these two beams, and then here have your photodiodes at the end. And we're going to put this on a dark port. We say when the two beams meet, there will be complete negative interference that will cancel out itself. But suppose I put a little phase shifter in there, just a glass plate. And what happens, I get a little phase shift to this. And then, of course, I could measure, for example, the thickness of this plate because it has a different refractive index. I have an effective path length change because I inserted a little phase shifter. Now, what if I don't put in a phase shifter? What if I don't put in a solid, but what if I put in a fluid? Well, if I put in a superfluid, it has quantized density fluctuations. And what's happening, if you imagine, if you have to think about it as a variant refractive index, and what's happening, the laser light coming through, because the density has variation, it has a delta rho or delta n, whatever you call it, it has density fluctuations, and you can directly couple these density fluctuations at the point of interaction. You can couple these and transfer it to phase fluctuations in the laser beam. And there is your detection scheme. And the power of interferometry, of course, is well known. So you don't have just a detection scheme, you have one that has enabled, for example, the gravitational wave detection. So it's a fantastic tool which has been developed and enhanced tremendously. So it's a fantastic setup. So I have not much time. You have to, of course, also see when you have an accelerator on a linear trajectory, on a circular trajectory, can you actually express that whole thing with a single temperature? And we did the calculations. And yes, there are situations where, you know, the spectrum is indeed described by a fixed temperature or a part of the spectrum. Now, when you do the modeling, and I really run out of time, I just want to say what you need to do is you need to really go through the details. You need to see how that laser light locally couples to your BSE. And of course, when you interact with this BSE, you can create attractive and repulsive regions in the BSE. So you have to put a bit more thought into it than just, you know, punching it with a laser light. But the first thing you also need to do, you need to write down your combined Hamiltonian, you need to linearize, and then you need to see what the effective field theory is. And can I actually see that as an not an Unruh-Dewitt detector, but as an analog Unruh type detector? We have done all this. Is published. You can see all the details here and below, published towards the end of last year. And so we give some more detectors of how not to disturb the superfluid by actually sending 2 laser beams in. You start with 1 laser beam, you have a modulator where the one is a red and a light detuned around a resonance. Resonance means absorption. But the effect is that you can cancel out any attractive or repulsive effect of the laser light interacting with your BSE. And you have to, of course, also consider how much energy can I put in, because of course, when you work with interferometers, you can make them very precise, but at the cost that you have to have a high intensity. But whenever you shine light on a medium, you also have absorption. And so there comes all this, is a fine balance, and you need to think you have to go beyond the shot noise, and you have to make sure that in all of your parameter space, there is a particular part, and we did the calculation, and on paper, it should be possible. Right, how much more do I have?
You already over time, so it's you and your question section now. So it's like 2 minutes until the end.
You know what? I just dropped that. It doesn't matter. I would have talked about this, but I don't need to talk about it. I just stopped. Okay, so I just want to now sum up. I haven't managed to talk about all the things. I didn't talk about the quantum black hole ring down. Apologies for that. I have to shorten the talk. I just take too much time. But I think I just want to end like who is behind all this is a big collaboration where we really work together. What is the difference? We have the people working on fluids, superfluids, optical systems, theorists working on superfluid helium and ultra-cold atoms physics, but we also have direct input from people coming from cosmology and black holes. So while we go along, of course, the idea is to provide, for example, high-level modeling for the false vacuum decay, to describe and understand better what's going on in these laboratory-based experiments. But then also, while we're developing the tools, we then will apply this back to the gravitational systems, so that we just make sure the stuff we use to solve that works, has been tested, at least in this little loop applied to these condensed matter systems. But then, of course, once you have established that, it will give you some impact of how to relate it back to the gravitational systems. And so now I just want to mention, end with this side by citing Albert Einstein, and I think this growth comes through analogy, through seeing how things connect rather than only seeing how they might be different. And so there were some discussions the other days, you know, of the value of the analogy and what it is. And I'd just say that what we learn from these analogs, that the mathematics is not just beautiful, it's very powerful. And the mathematics that has been developed for black holes or cosmology, they're actually applicable to other systems. And if you have a good analog system where you say, well, these, you know, in these two limits, the dynamics or the physics should be the same, you can actually test your toolboxes. And then there is, as I would say, one more step here. And this one more step is well, no analog is a perfect analog. And I would say this is its biggest virtue. And why would I say something like that? Is because, you know, not whatever quantum gravity really is, right? Quantum field theory in curved space-time is for sure not a bad, it's a reasonable assumption. But we also say, well, there might be something more. It might be that you get some corrections. It might be that, you know, something a little bit bigger. So it shouldn't be precise. And I think this whole idea that you have a system which is not ideal, is not perfect, has many deviations, which you can actually control, switch on or switch off, or make big or small. What that tells us, what we have seen in the analogs over the last 5 years, is in experiments that our characterization of this effect actually matched what we've seen in the experiment. And what this means, and many things in the experiments we couldn't even take into account in our modeling. There's always a simplification. But what we have never seen, not a single time, that a process would completely break down. It would survive. It might have a modified spectrum or whatever, but it would occur. There is a certain robustness there, and that's very trustworthy. As a message for things we cannot directly interact with, whatever the modifications and corrections are, whatever is not true, but at least we have seen that these calculations are really useful for a broad range of other systems. And with this, I'm stopping. Thank you very much.
Thank you very much for the beautiful talk. Okay, we have I think we have some time for a couple of short questions. So if anyone wants to ask, please unmute yourself. And okay, I have one quick question, maybe technical, related to this two fluid picture, where you have if you go back in your slides, the coupling GIJ between two bosonic fields, and then you said that so these couplings, they so do you have a control of these couplings, or in experiment, or?
So, right. So you have control over this. So the transition rate, as I said, is given by external fields. When it comes to scattering, of course, there is, like, you know, the atoms scatter with each other. Mm-hmm. So the kind of atoms you're choosing. So some things are given by the choice of atoms, for example, the bosons, which ones you're choosing. So it's a combination. You have to, so it's a combination of things. Some parameters are given, and others are effective parameters. They sort of appear and come out, and some are easily tunable and others are not. But yes, in principle, you should have enough tunability to set up the false vacuum decay. Mm-hmm. For example, you have the ability to make the mass stable or unstable. That's already known.
And when you write the Sine-Gordon equation, this parameter lambda, which you showed, it depends on this, right? It depends on the GIJ and nu, right? Or it depends only on nu.
Lambda only, the effective mass goes to 0 if this coupling is off, because then you have the symmetry, which is spontaneously broken when these things condenses and form a BSC. So only the presence of this last term here, that gives it a mass. And lambda only enters in there. So this term that gives it a mass, that's the one you have to modulate with the high resonance frequency.
Mm-hmm. And my last question, so you showed this picture of vacuum decay, where you had this red and blue. The blue region is the initial vacuum state, and then red is what.
Yeah.
So so when from this big lambda parameter, there's some, I see that there's a cone, right? So Uh,
yeah.
can you comment like
And
why? Mhm.
yes, happy to do that. So what you form, so you have here what one calls, for example, let's go to first lambda equal 1.5. You have this. So initially, this is space, and on the x-axis and on the y-axis is time. And then you have everything blue, which means that your relativistic field is in a false vacuum. So it's metastable, stable, stable until some time you start to have this little blob forming here, which is what one would refer to as a nucleation event. And then it propagates out in space with the effective speed of light. And so inside everything is in the true vacuum. Now, interestingly, when you remember the Sine-Gordon potential, you don't only have one true vacuum. You're on this top of the potential, which with a little dip, a local dip, and then it could go to the right and the left. And what we see here is, for example, there are different interactions, right? So some have this sort of oscillatory behavior, some have the straight lines, and it depends if two neighboring bubbles form and are in the same or in a different vacuum. So exactly what we would like to study here is the late time behavior in this system. And what I should mention is this is 1 + 1, but the actual simulator we're building will be a 2 + 1 dimensional relativistic field theory. And then exactly then really having bubbles interacting, seeing if, how circular they are, how they interact, what the correlation measures we can form, what is really behind this nucleation process. Can we learn a few things? Can we learn about the calculations we do? And again, the simulations we're doing, can they actually, which are of course approximations and techniques, and is this what we will see in the experiment, or do we have to opt up our numerical game as well?